full screen.
Yeah, so I'll see if that works.
Maybe is it a Windows machine? Then Control K or Control L may work.
Did that work?
No. Or you can click on that arrow in the right hand side. It will actually push that screen to left side, a little bit right. Like organize pages in that arrow.
Right, so it went for full screen for me, but sorry, where?
Yeah, organize pages, that little arrow here.
No.
Here in the right side, you can see there is organized pages.
This one? No.
No.
Oh, down
middle,
here.
yeah.
Right.
No. Don't click it. Yeah. No.
What do you want me to do?
Yeah,
Just get rid of
exactly,
that? Is that what you mean?
So yeah, but control K or Control L is working.
Yeah, no, I did a Control L. I'm on a Mac, and it went to full screen for me, but it obviously didn't work for you. But is it? So I can't see what it looks like. So what's? Yeah. I mean, I know you're seeing the. Yeah. I could just try going to full screen, and then I'll tell you what I'll do. I'll quit, I'll escape, and then go to full screen, and then try sharing again.
Yeah, I guess.
I'll try this. Maybe
share once more. Let's see. Yeah, this is the best one. Yeah.
Okay. All right. Okay.
Yeah. So let me go for the introduction of Professor Wiseman, and this is the second talk, plenary talk in this session. And Professor Wiseman is a theoretical quantum physicist at Center for Quantum Dynamics, Griffith University, Australia. He heads the Center for Quantum Dynamics at Griffith University. He is known for his work on quantum feedback control, quantum measurements, quantum information, especially quantum steering, open quantum systems, and many other topics in quantum foundations. He is a fellow of the Australian Academy of Science, a fellow of American Physical Society, and fellow of the Optical Society of America. In 2022, Professor Wiseman was awarded the AIP Walter Boas Medal for Excellence in Research. With this, I welcome Professor Wiseman to deliver his talk, and the title of the talk is Can Super-radiant Lasers Achieve the Heisenberg Limit for Laser Coherence? Professor Wiseman, now dash is yours.
Thank you, Professor Raj, and thank you to Professor Panigrahi and all the organizers for inviting me to give a talk here. So, so yes, because one of the themes this year is quantum optics, I decided to give a talk which is really quantum optics, but we'll see that, yes, that it has some flavors of quantum information and quantum technology as we go through. Okay, so I've given a slightly different title, the Heisenberg limit for laser coherence, so to explain that first, and then with preliminary results for super-radiant lasers. So I have quite a few co-workers, so I'll start with Dominic Berry. So he and I hold funding for this project through a discovery project to the Australian Research Council. So as was said in the introduction, I'm at the Centre for Quantum Dynamics at Griffith University, and that's at Brisbane and the Gold Coast in Queensland, Australia. And Dominic is in the Department of Physics and Astronomy at Macquarie University, which is in Sydney, Australia. And everyone else here is a member or a former member of my group in the Center for Quantum Dynamics. So Trav Baker was a PhD student, Nariman Sadatman was a postdoc, And so they will be irrelevant to the general topic I'll be talking about, as will Lucas Ostrovsky, who's a current PhD student. And then another current PhD student, Ori Somek, is the one who's been working on this particular topic to do with super-radiant lasers that I'll spend quite a bit of time talking on. And I should say that if there are, if there are really important questions that people want to ask during the talk, because there's something that I'm using some term that doesn't make sense to them or needs to be clarified, then I'm happy to take that. I guess I can see the chat, so maybe if something comes up in there, I'll pause if it seems like something that I need to clarify. Okay. Whoops, I think my I don't know how my timing is going. But yeah, let's get a move on. Yep. Oh, I should check. Can people see the cursor if I move it around? So there's a little hand that I'm moving around. Yep. Yes. Okay, good. All right. So yeah, so the general topic is in this area of Heisenberg limit for laser coherence. And so this was the title of a paper that I and these co-workers had published a couple of years ago now in 2020 in Nature Physics. And this is some artwork. Actually, are you seeing this this thing that I'm moving around now? Is that visible to people? To do with screen sharing and whatever? Anyway, I'll try. In case it is, I've moved it off. All right, don't know why I bothered asking. All right, so yeah, so this is some artwork that we had done when the paper was published, which is sort of cute. Doesn't tell you a lot about what's really going on, but that's what I'll begin by talking about. So really, I thought that the most important thing to do would be just go through this title and explain what are the terms in it, and yeah, in the context that I'm using it here. Okay, so whoops. Oh, okay. So there are the people who were involved in this bit of work. So that's Trav, me, Naraman, and Dominic. Yep. So let's start at the end of the title with coherence. So this is a word that has many meanings, of course, and I'm using it in the optical context here. So we're talking about optical coherence, but I don't mean, as you might think, a mean field or absolute phase of the field, because that's not something that it would be physically meaningful to require a device to produce. Yeah, it would not be useful to think of coherence that way. So what do we mean? We mean something, a property of a quantum field that allows it to act as if there is a mean field, say. So basically that allows it to act as an effectively classical phase reference. And to do that, it's been understood for quite a long time. Essentially, all you need to do is have a large number of photons in a particular mode. And then by splitting that, you can create a phase reference between two different sites. So the measure of coherence, which we're going to use, and this is a very fancy letter C, that's what I'll be using throughout, is just this, the mean number of photons in the most populated mode. Okay. So this, just to make a perhaps obvious point, is that this measure of coherence combines both particle and wave natures of light, because it's talking about the number of photons, which is obviously particle nature, but it's also talking about a mode, which is a wave aspect of light. Okay, so in particular in this talk, I'll be interested in fields which are beams of light being produced by laser, as we'll see. And so if one has a beam of light with time stationary statistics, then in the typical situation we'll be talking about, this coherence evaluates to the product of two numbers, this curly n, which is the symbol I'll be using for the photon flux, just meaning the photons per unit time, just that, and then tau coherent, which is the coherence time. So hopefully that makes intuitive sense, that I take the number of photons coming out per unit time and multiplied by the coherence time to get the number of photons that are mutually coherent. And for a beam of a particular type, one can show that this is the correct expression given this fundamental definition as being the mean number in the most populated mode. Okay. All right, so then moving backwards to the next step, laser. What do we mean by laser? So, I mean, probably a lot of people have studied some laser physics, but I want you to forget most of what you've learned in that, in terms of defining perhaps what a laser is, because I want to appeal to a very general concept of what a laser is as being just any device that creates an optical output beam with high coherence from inputs that have negligible coherence. Okay, that's, I think, fundamentally what a laser is. And so then the question comes up, how does a laser do this? How does it take low coherence and create high coherence? Well, one thing it has to do is store a large mean number of excitations, okay, at the frequency of the beam that it's producing. They don't have to be photons. They could be photons, but these excitations could be stored as atomic excitations or excitonic excitations, but whatever way, yes, you have to have a large number of excitations stored inside the laser. And then one can ask, well, what does the number of excitations stored in the laser imply for the coherence of the laser output? Well, this is something that Schawlow-Townes famously worked on a long time ago in 1958. In their paper where they essentially introduced the idea of what they called an optical maser. And they showed there that the coherence time for an optical maser, or a laser as we would say now, when you're in the limit where this large number of the number of excitations is large, coherence time is of order mu divided by kappa, where kappa is the bare cavity line width or decay rate of the cavity. Okay, but then also the flux of photons out is that decay rate of that cavity times the mean number of photons in the cavity. So multiplying those two things together, one gets the scaling of the Schawlow-Townes limit for the coherence, which then the kappas cancel out, and one gets that this coherence for in the Schawlow-Townes limit is equal to something scaling like mu squared. So that's what the big theta notation means, that it's within their model, it's upper bounded by this scaling, but also that it's achievable. So they actually, gave a laser model which achieved this scaling here. So that's what that means, as opposed to this O just means an upper bound. Okay. Right. So we've got covered coherence, we've covered lasers, and now moving on to Heisenberg limited. Right. So in general, now forgetting about lasers or coherence, what we're talking about with Heisenberg limits is, or in general with quantum limits, is the idea that we have a device that we want to do something, right? It has a task to perform, and quantum theory sets out limits on how well that task can be performed, depending on the resources available to that device. So for example, the energy or the power that it has. And now a standard quantum limit is a limit of this sort that's derived making standard, inverted commas, assumptions about how the device must work. And that's opposed to a Heisenberg limit then, which is, again, really just means the ultimate limit. For historical reasons, it's called a Heisenberg limit. The ultimate limit that quantum mechanics allows, and we say that there's a quantum enhancement when the Heisenberg limit scales better in the resource than the standard quantum limit. And the most famous example of this is the quadratic quantum enhancement of the Heisenberg limit over the standard quantum limit in the task of estimating a static phase, where your resource is the number of photons that pass through the phase shift that you're trying to estimate. And so the important thing here is that we prove that the STL is just an SQL, okay? The Schawlow-Townes limit, which I showed you on the previous page, is just a standard quantum limit. It comes from standard assumptions about how lasers work. It's not the Heisenberg limit. And what we show in particular is that there is, again, a quadratic quantum enhancement possible for this task of the production of laser coherence. Okay, so this is not a Heisenberg limit in the sense of a metrological task, although as we'll see, there is a link to metrology. It's using that term to just mean, you know, how well can you achieve any task, and the task here is to get as much coherence as possible given the resource of the number of stored excitations in the laser. And so what this means is, yeah, the Heisenberg limit for a laser, what we prove is that that scales like mu to the fourth, not like mu squared as for the standard quantum limit, or yep. Okay, so that's yeah, a summary of what we did in that that 2020 paper. But I'm going to begin by going through in a little bit more detail about what was in that paper, because it's still necessary to really understand some more of that before we get into the topic of superradiant lasers. So I will yeah, basically I'll start with that. Then I'll talk about physical realizations in general, and the superradiant lasers will come up in the second one of those, and then I'll complete. All right, so this proof that we had in this paper in 2020 of the Heisenberg limit, how did we do it? Well, we had to begin by being a bit more specific about what we mean by a laser than just this intuition that it's something that takes no coherent inputs and creates high coherent outputs. So we had to write down some fairly yeah, precisely defined mathematical conditions that a laser has to satisfy, but most of them are pretty easy to understand. So the first one is just that a laser is something that produces a one-dimensional output beam. So that means that the beam propagates away from the laser in a particular direction at a constant speed. And for simplicity, we'll say that it has a single transverse mode and a single polarization. So what that means is that the whole beam can just be described by a set of operators parameterized by some real parameter, that T. And B of T is the annihilation operator. Yeah, well, it's some type of annihilation operator, and we're going to normalize it so that B dagger B is the operator for the flux of photons. So the mean, oh, well, I shouldn't say mean, the photons per unit time operator is B dagger B. Okay, and I can think of this this time argument as being the time at which the bit of the beam that's relevant got emitted from the laser. Okay, so here's the laser over here, and the beam is propagating in this direction. So the B of, like, if I sit at a particular point in space here, at some particular time, the B of T that is I'm experiencing, if you like, that describes the field here is the B at the time at which that beam was emitted. So that's going to be, if I'm talking about at time yeah, T, then that would actually be the capital T. No, hang on, which way am I? I've got myself all confused. Yeah, so tau must, no, yeah, so tau is the length, must be the length of this essentially in time. So C times tau will be the distance from the laser. And so I'm looking at the B emitted at an earlier time, which was capital T minus tau. Okay. This is going to be important in the next slide, because the second crucial condition we need is one of endogenous phase. And this really captures the idea that you're not feeding coherence into the laser, rather the laser itself is producing the coherence. Okay, so endogenous phase, the coherence of the beam proceeds only from the laser. And mathematically, how we define that is that by imposing at some time T, capital T, minus tau, an optical phase shift on the laser state, that's equivalent to instead imposing at the later time, capital T, the same phase shift theta on the laser and also on the beam emitted in that subsequent time, from the earlier time to the later time. Okay, so even more mathematically, that's saying that like there's some operator n hat C, so the C here stands for cavity, but we're not really making any assumptions at all about how the excitations are stored. We just have some operator, which is a number operator for the excitations. So the eigenvalues of this operator are the natural numbers, including 0. And right, so to impose a phase shift on the laser at that earlier time, we do this unitary operator. And this condition is saying that that's equivalent to, at a later time, doing the doing the same phase shift on the laser cavity, okay, at that later time, and then doing the phase shift on the part of the beam that had been emitted in the meantime, right? So if this, if for example, one were just putting in coherence from some other laser into a laser, then this would not be true. Then like just changing the phase of the laser wouldn't achieve this transformation of changing the phase of what comes out of the laser if it was being pumped by something else. So this really guarantees that whatever the coherence of the output is, it's coming from the laser itself, which is what endogenous phase means. Okay, so that is, it's a little bit complicated, but it's absolutely necessary. Condition 3, right, is very easy to understand. Stationarity just says the statistics of the laser and the beam are invariant under time translation in the long time limit. And one consequence of that is that I can ask what is the mean of this operator NC, this number of excitation operator that appeared in the previous definition. And yeah, that's going to have, therefore, some particular long time limit. And I'm just going to call that mu. So that's where the parameter mu enters into the problem. And then finally, condition 4 is another fairly complicated one, and I won't actually go through all of the mathematics to describe this. But what we need to, before we actually get to the condition, we need the concept of Glauber coherence functions. So I'm hoping most people have heard of that. They're basically, so for historical reasons, the first order Glauber coherence function is a 2-point correlation function in this one-dimensional beam. I mean, in our case, it's one-dimensional, so it's a very simple thing. And the second order Glauber coherence function is this 4-point correlation function in the beam. You'll note that they're defined with an equal number of B daggers and Bs, which means that these things don't depend on any absolute phase of the beam. Okay. Right, so the first one is all that you need, in fact, to work out the coherence of the beam. With the assumption that it's a stationary beam, it turns out that the coherence is just given by the spectral peak. So basically, I take the Fourier transform of G1, and that gives me the power spectrum of the laser beam. And then I just ask, what is the maximum over frequency of that power spectrum? And that is, in fact, exactly the coherence as defined earlier. All right, so that's that. And we'll get to G2 in a little while. Okay, so that's the first sort of background we need for this. The second background we need is the concept of an ideal laser, and so this was something that was really introduced in the 1960s by quantum optics theorists like Scully and Lamb, Lax, and Louis Zell. And the essential, they all, I'm not quite sure how independently, but came to the realization that an ideal laser is one where the beam is well described by what I'm calling a stochastic coherent state. So it's a coherent state with amplitude beta of t, where beta of t has a fixed magnitude but has a phase, right? So appearing up here in the argument, a phase that is diffusing in time. So this W of t is a Wiener process or Brownian motion, for those who've heard it called that. And so the amplitude, or the amplitude squared, is just exactly the photon flux, the mean photon flux that we've also talked about before. As I said, W is a Wiener process, and the other parameter here, L appearing, is what's called the line width of the laser. Okay, and it turns out the relation between the coherence and the flux and the line width for this type of beam is exactly given by this. Okay, so with all of that, we can then define what we mean by ideal Glauber. Well, okay, condition 4, which is ideal Glauber 1-2 coherence. Okay, and that says that the stationary Glauber 1 and Glauber 2 coherence function well approximate those of an ideal laser beam. And what we mean is one's calculated where instead of these operators appearing here, I just replace them by beta of t and beta star t, respectively, for the annihilation and creation operators. So that's the idea of how we calculate those. And then there's a mathematical sense, which I'm not going to get into. We require this G1 and G2 to well approximate that. So essentially, the assumption is just that the beam we're talking about that is close to that of a standard ideal laser. Okay. Yeah, I might. Yeah. So very briefly, yeah. So what G2 has to do with is many things, but one of them is the Poissonian, is the photon statistics. So in this case, with this assumption, it means that we actually have something close to Poissonian photon statistics. And likewise with G1, it turns out that means we have close to a Lorentzian power spectrum. Okay, or just, yeah, exponentially decaying coherence, if you like, coherence function. Okay. So given all that, we can derive this upper bound, okay, show that there is the maximum possible coherence which can be achieved is of order mu to the 4, okay? Now, I think given the time, I will skip through the details of that, but just to say that the actual proof is done in this surprising to me. I mean, I didn't imagine originally that we'd do it this way, but essentially we apply results from quantum metrology, and it's a very quantum information-y type argument in that we imagine various parties who have various tasks to do, and they've got this laser, and they can make choices about what to do, and we can put bounds on things. So yes, I won't try to explain how all of that works, but just to say that we need so maybe the first things we need conditions 1 to 3 on this slide to prove that one type of measurement can never be better than another type of measurement. And then we use condition 4 to actually derive a particular mean square error. That's the one with all the properties of the beam. And we put it all together and we end up with this bound here. Okay, we prove that the coherence for any device, right? There's no assumption whatsoever about how this device works. All we've assumed is that it satisfies those 4 conditions, and we're able to prove that the coherence of the output is bounded above by roughly 3 times mu to the 4th. Okay, but now that's just an upper bound. That's not actually a Heisenberg limit until we prove that it's achievable. And so then that's the next step. Okay, we want to introduce a model, and it's just a very theoretical model where we can actually achieve that scaling. Yeah, so it doesn't have to be the most general model or anything to prove the Heisenberg. We just need to prove that there is some model which will achieve what we want to do. And so the model we use is a finite dimensional, a d-dimensional system. So this is this is now the number operator. And we use a standard sort of master equation to describe this. So this is my laser. It has some sort of energy has to come in, and energy has to then come out in the beam. And so the energy coming in is described by a gain operator, and the energy coming out is described by a loss operator. And these are assumed to have only non-zero elements connecting neighboring photon numbers. Okay, so the gain obviously can increase the photon number by 1, and the loss can decrease it by 1. So it turns out that along as all these elements are non-zero, then there's a unique steady state, which is given by this recursion relation. And then we can prove that this model, by definition, satisfies conditions 1 to 3 exactly. Okay, so we don't need to say any more about that. Condition 4 is trickier, but what we find numerically, that's the one to do with the Glauber coherence functions, is that we can satisfy that by a very simple choice for the gain operator of 1, right? Which just means that essentially the amplitude to go up from one photon number to the next photon number is totally independent of what number you are in at the present time. That makes sense. So that's that's a particular assumption. So with that assumption, then we can optimize then the loss operator, and we essentially do that by actually optimizing over the steady state distribution, because there's this if I know these things, then I know the steady state distribution, so it's easier to actually optimize over that, and that gives me an equation then for the loss operator. And it turns out that this is a very good ansatz for the optimal steady state distribution. It's a very broad distribution in number, okay? So it's much broader than Poissonian. So this means that the mean number, it's symmetric, so the mean number of excitations is roughly d/2. And then if we plot, then from our model, we do an exact numerical calculation of the coherence of the output beam created by that our particular model. And we find it very well fits a power law in the dimension of the system, which means it's a power law in the mean number of excitations. And the particular power law we find is this, okay? So 0.062 times mu to the fourth. So it's the coefficient here is a lot smaller than the 3 that we found as the upper bound, but the important point is that the scaling is the same. So we have proven that there is a Heisenberg limit scaling for the, we've proven that the Heisenberg limit scaling is mu to the fourth, and so therefore there is a quantum advantage, right? Because the standard quantum limit was mu squared, and we have a quadratic quantum advantage in this case. Okay, so that was what was in, oh, well, no, there's a little bit more in the first paper, but yes, we had a little bit more in the first paper after the first round of referee reports. The referee said, this is all very nice, but how could you actually imagine doing this? And so we came up with, in the paper, the idea of it would be in principle possible to do this in circuit QED. Okay, so one might say then it's actually a Heisenberg limited maser rather than laser, because, and I gather this was talked about quite a lot in the last talk. With the circuit QED, we're talking about microwave frequency electromagnetism. And again, I won't go through the details, but we just showed that with standard coupling Hamiltonian, so a Jane's Cumming Hamiltonian between a microwave cavity, on-chip microwave cavity, and some qubits produced by, well, whichever way you want to produce qubits in a superconducting system. In principle, by just changing the detuning of these qubits, it would be possible to transfer energy in and out of the cavity in the way exactly as described by those gain and loss operators. Essentially, you can dial up any gain and loss operators you like in principle, right? And therefore, one can dial up the ones that we require for our Heisenberg limited coherence. Yeah, and that's probably all that I want to say. So as I said, we very much did that as an in principle proof that it could be done, and then it turned out being done independently and published a year after our paper. There was this group in the US who also were thinking about, can you go beyond the Schawlow-Townes limit in some sort of superconducting circuit QED system, and they came up with a completely different proposal, which surpassed the standard quantum limit. Okay, but it did not actually achieve the Heisenberg limit, because when they did their work, they weren't even aware that we had proven that there was actually a Heisenberg limit. So they were happy when they showed that they could get a mu cubed scaling. But yes, it's not actually the Heisenberg limit scaling. So yes, it's a very different architecture. I'm not going to talk about that at all because it's not my work, but just to let people know. Okay, but then that's not the end of the story, because with the new grant that we got, we now have a collaboration with a French superconducting group. Well, two groups really. So the experimentalists Audrey Bienfait and Benjamin Loire at ENS Lyon, and a theorist, Mazia Mirahimi, at ENRIA in Paris. And yes, we are working with them to try to figure out what would actually be a practical way to try to surpass the standard quantum limit in a superconducting laser, and that hopefully they'd actually be able to demonstrate that. But that's early days yet. And yes, my PhD student Lucas Ostrowski is on the team working with them on that. Okay, so that's the end of the circuit QED part of the physical realization, and I want to spend more time now on the second one, which is in cavity QED. So for anyone who doesn't know, QED stands for quantum electrodynamics. So cavity QED was the term introduced, which just describes having a strong coupling, a regime where you can have strong coupling between individual atoms and photons by confining the photons to a small cavity. And then circuit QED came along much later and said, well, we can do this much more easily because we can make artificial atoms with, you know, whatever parameters we want. But it's still of interest, I think, very much to consider the original cavity QED situation, because that's what we need to do if we actually want optical frequency laser beams as opposed to masers, right? And for a lot of applications, one really does want optical frequency. So then that's what we are still working on. So then this is my other PhD student, Ori Somek, who's working on this. And right, so the essential idea, the particular cavity QED system which we are looking at is building on the idea of a super radiant laser. Okay, so this is a cavity QED system comprising n atoms identically coupled to a single mode, where that mode is then heavily damped, which means that effectively one has collective damping, pardon me, of all of those atoms. So instead of in a standard laser where we might be storing our excitations as photons, and the lowering operator would be the annihilation operator, which looks like this. In a cavity QED system, the lowering operator, we're just going to call this, oh, okay, there's a bit of, well, okay, J or J minus is the sum of all of the individual lowering operators for the atoms, up to capital N of those. Now you might say, well, why would that be useful? Why would it be a good thing to store excitations in atoms and have them collectively damped like this? Well, here is, so that's the question. Why might this be useful? Well, this graph is meant to explain why. So I'm plotting three things here. So this A of N is the coefficients for the standard annihilation operator for harmonic oscillator, okay? And so that's this yellow curve here, and this is plotted with little n, going from 0 up to some maximum, okay? But so this is just a parabolic shape here. Somebody's drawing on my screen. Can they? That was surprising. Unless, I don't know, I don't recall doing that. Okay, the Hn, and H I guess stands for Heisenberg limit here. This is plotting these elements for the loss operator, the particular loss operator that was gave us the Heisenberg limit in the model that I introduced like a few slides ago, right? The completely theoretical one that we said, okay, we just have to come up with some model which can achieve this mu to the fourth scaling for the coherence. And the one we came up with, it has this very weird looking profile for the loss operator. It's almost flat. It looks flat, but actually there's a slight slope to it here. And then it drops off to 0 at 0, because you can't obviously go any lower. But it also goes up really quick, really high at this maximum n, which was related to the dimensionality of the system. Okay, so that's the crazy one, which we assumed to prove that a Heisenberg limit was possible. And then the Sn here, and S I guess stands for super radiant, is what this particular operator looks like. Okay, this collective lowering operator for all the atoms. And so it's this blue one here, right? So it's quite different from both of them. It looks sort of similar to the yellow one here, but when I get to this regime just about there, it's actually very close to the green one, right? It's very close to flat. And so it's actually not in the middle that it's closest. It's just very slightly on this side. This is for some finite n. So that suggests that if we were working in a regime around here, then maybe we could get something like the Heisenberg limit because we're matching this flatness, which seems to be key to the loss operator here. Okay, so Okay, yeah. So the idea then is, have I skipped something? No. Okay. So I'm going to begin by just telling people, not reminding really, because I haven't had a chance to talk about this, but the standard model, the model that actually achieves that standard quantum limit for the laser looks like this. So it has a damping operator, linear damping, that is what gives rise to the beam. And it has this weird looking gain operator here, which, well, does the standard gain for an ideal laser far above threshold. So I'm not going to explain where this comes from, but yeah, what this gives is, as I said, this gives linear loss, which means if I look at the rate of change of the mean number of photons, I get a minus kappa times n bar, the kappa coming from here over there, moving it to this side. Oh yeah, so this is an equation for the Lindbladian operator, I should say, okay, or Liouvillean operator, super operator. Right, so I get linear loss, and then this model for the gain gives me exactly constant gain, okay? So not linear, as I'd have in a linear amplifier, but constant gain because it's modeling far above threshold. So in this particular case, the mean number turns out to just equal this parameter nu. And as I said, this actually gives the standard coherence, which is 8, turns out to be 8 mu squared, that's the specific coefficient, which we call the standard quantum limit, therefore. Which is a little bit different from the Schawlow-Townes limit. It's actually, yes, the Schawlow-Townes limit is actually 4 into mu squared, or even more correctly, 4 into mu plus 1, because that one we can work out exactly, because their model was basically just a linear amplifier. So it turns out that that's what Schawlow-Townes limit means, which is the same Powell law, but a different coefficient. Okay, so that's just all standard lasers. Our proposal here is to superize this, right, by having not only super radiance, okay, so I'm replacing the loss operator by J minus operator, but I'm also going to replace the gain of the creation operators here by the raising operator, the collective raising operator. So this is not your ordinary super radiant laser. This is actually what we could playfully call a super-duper laser, because both parts have been made super, right? I have both collective loss or collective output, but also collective pumping. So this pumping term still gives the same sort of constant gain. So again, gamma times nu is the rate of gain, but I have a highly nonlinear loss now because of this J minus here. So the question is then, well, if we just for the moment just assume that we could produce a model like this, what sort of coherence can it achieve if I optimize this parameter nu? And so, yeah, we have, it turns out there's some interesting dynamics for this. So this is like a sort of semi-classical analysis of what's going on. So as I said, the gain, okay, so what I'm plotting here, I'm plotting if I had a particular number of excited atoms, and here I'm using a spin representation. So so little m here goes from minus j to plus j, and minus j means all of the atoms in the ground state, and plus j means all of the atoms in the excited state. And so the number of atoms is 2 times j. Okay, so this is a very standard spin representation. This is jz, just the sum of the little sigma z's. Okay, and so so the gain is actually flat. It doesn't matter what number, how many excited atoms you were with that model of gain. The probability to go up by 1 is the same everywhere, whereas the loss has a shape which looks like this. So this is essentially the same sort of shape that we already saw here in blue, but plotted in a slightly different way. Okay, and so if one looks at where the gain and loss are equal, those are going to be fixed points. But this one, semi-classically, is stable, whereas this one is unstable, because in this one, you gain, it tends to force you this way, right? Because gain always takes you up. Loss takes you down, but as you go this way, you get less loss. Okay, and so you're going to just collapse towards another point down here, which is where the gain finally goes to 0. And so that's another stable point there. So I have a semi-classically a stable point here, an unstable point there, and a stable point here. In the quantum case, things are more interesting. It turns out, so in terms of a parameter, so I should say, so the maximum gain, maximum loss, so the maximum rate of outputting photons in this case is this parameter gamma times n/2 squared, and that square is characteristic of superradiance. Okay. And R, or R squared as it appears here, is a scaling of how big the gain is compared to that maximum loss. Okay, so that's what this R squared does. So it turns out for R less than a critical value, R naught, the semi-classical point, stable point, is stable in quantum mechanics as well. So you get a solution around here. For R between this value and some other value, which actually depends on n, it's metastable, which means that if you start here, you don't actually stay there forever. You eventually end up over in this other stable point. Okay, so that's what metastable means, and that's what these graphs are showing. And then finally, if your R is too large, it's just totally unstable, and you go to the excited state very, very quickly, right? Yeah, it's not metastable at all. The metastability means that you stay in this state for potentially a very long time, and that's what we actually yeah, so that's what we calculate here. So maybe I'll just start with this. So as a function of R squared, the metastable time can be truly enormous compared to the coherence time of the laser, which is the other timescale we're interested in. So in this metastable regime, it's not, we can't just say, oh, it's metastable, it's uninteresting, because actually if the metastable time is like 10 to the 30 or even 10 to the 3 times the coherence time, then really we can pretty much assume that the laser stays in this metastable state, you know, for many coherence times, which, so we're going to get all the coherence we want out of the laser, and then something goes wrong and we'd have to restart it. Okay, so it turns out that we really want to be in this metastable time, because as metastable state rather, because as R squared, if I just look at the stable solution, so that's this solid line here, so the coherence increases, the coherence relative to the Schawlow-Townes limit starts off at 1 when I have very low pumping, so it's equal to the Schawlow-Townes limit, goes up to 2, which is the standard quantum limit as R squared increases, goes above 2, which is nice, as R squared goes up, so I'm beating the standard quantum limit here. But then if I just follow the stable solution, beyond a certain point, it collapses, because yeah, that's what the stable point, it just all goes up to the excited state. But actually the relevant thing is the metastable, if the coherence time, if the metastable time is long enough, then the relevant thing is the metastable state. And you see that as R squared goes up, the coherence just keeps going up and up and up. And as long as it stays in the metastable state for enough time, that is going to be a relevant number to be calculating. Okay, so we actually did this analytically in the asymptotic limit. So Ori did these calculations, showed that if we choose R very slightly less than 1 with this particular scaling in n, then the log of the metastable time to the coherence time scales like this. Okay, so that's a log, which means that the actual ratio is the exponential of this. So as long as this is even moderately large, the ratio is huge, right? And so looking at what this means, it means that, well, as long as Q is strictly less than 2/3, this thing scales like n to some positive power. So for large n, that's going to be large, and this ratio of the metastable time to coherence time will be enormous. So essentially that means, yeah, so as long as therefore we choose Q to be less than 2/3, that's going to be positive, and I can use the metastable state for sufficiently large n. And so then in that limit, with choosing these things here, it turns out the line width of the laser scales like this. So that's 1 over the coherence time. The flux scales like that. So that's the gamma n/2 all squared, which gives me a coherence in the end, which scales like n to the 2 plus q over 4 beta. Beta is this parameter up here. And if you remember, so that can be as large as, almost as large. So remembering that, actually, I don't think I said it here, but the mu is basically equal to n/2. So this is scaling like mu to the 2 plus q, which can be almost as large as mu to the 2 2/3. In other words, almost as large as mu to the 8/3, which is clearly a different scaling, a higher scaling than the standard quantum limit, but not the Heisenberg limit scaling, which would be mu squared. So we have surpassed. So in terms of the question, which I put, I think, as the title to my talk in the program, the answer is no, it cannot, it would seem, reach the Heisenberg limit scaling, but nevertheless, it can surpass the standard quantum limit scaling. So I think it's still very interesting. Okay, now, again, to leave time for questions, I think I'll probably skip a bit. Just to say, so we have a specific model where this could be realized. So we actually have, we consider like an array of 3-level atoms coupled to 2 cavities. So this is the complication that one needs: one cavity for the gain and a different cavity for the loss. And moreover, to achieve what we need with the gain, one has to use feedback control to turn the to turn this excitation field on and off, depending on getting a click in this detector here, which basically tells you you've added a photon to the, well, not a photon, you've added an excitation to these atoms. We assume that these are all in a perfectly symmetric state, so everything is perfectly coupled. And yeah, that's how we get the model. We show that then by eliminating various things, we end up with the model that we started with. I think I'll just skip through this, but just to say that this is quite different from what one might call an ordinary superradiant laser. So there's been a lot of work. So for example, this PRL from 2009 on ordinary superradiant lasers, where it's only the loss, if you like, that is superradiant, but there is no collective gain. So they are already known to be able to achieve extremely low line widths. But what we show is, so with a particular model, so one can achieve even much smaller line width, sorry. So going from a sort of millihertz to actually microhertz. And yeah, so we can get roughly 50 times, for reasonable looking parameters, 50 times narrower line width, and a coherence 100 times bigger than with the standard ordinary ones. And yeah, I don't think I have time to go through these pictures. Okay, so but yes, I mean, you've all seen them, so feel free to ask questions if you want more details. And I have other pictures at the end if they might be useful for explaining other questions. Okay, so to conclude, right, I will start with the summary. So the laser coherence, which we've defined as the number of mutually coherent photons in the beam. Well, maybe I didn't say this, but yeah, I should have said, this is why we're interested in this, is that this is a key resource in classical and quantum technology. You need highly coherent beams in order to do all sorts of things in both classical and quantum technology. And what we showed in 2020 is that beyond the standard quantum limit, which is at the coherence scaling like mu squared, in terms of the mean number of excitations in the laser itself, mu, there is a quadratically better Heisenberg limit. In other words, a coherence scaling like mu to the 4th. And our theorem then proving that we get this bit of scaling places just 4 conditions on the laser and its beam, and you saw what they were. We constructed a model achieving this quadratic enhancement while satisfying all 4 conditions, and so that's how we proved it as a Heisenberg limit, right? So first we proved that it's the maximum you could achieve, and then we proved that it's achievable. Okay, then we showed that it could, in principle, be realized in circuit QED, and then, as I've been talking about most recently, in cavity QED, if you want to go to optical frequencies, things are more constrained, but we came up with a model for a super-duper laser that could still surpass the standard quantum limit scaling, even if not at the Heisenberg limit, by having a scaling like mu to the 2 plus q for any q less than 2/3. All right, and then I'm not sure how the timing is going. I could stop at this point, or I could say a little bit about the ongoing work that we have. So Chair, what should I finish this slide?
Yeah, you can take 5-7 minutes more. Okay,
well, this will only take a few minutes. So yeah, we should have time for questions. That's good. Yeah, so just to say a little bit about other things that are going on in this area in my group. So you may have noticed that the condition 4 was by far the most one that needed the most explanation, this ideal Glauber coherence. So just to remind you, that was that the beam's coherence functions well approximate those of an ideal laser beam. So it feels a little bit unsatisfying to have this condition. It's a bit like Euclid's fifth postulate in geometry that was sort of complicated and people spent a lot of time, millennia that people spent trying to figure out if they could do without it. And so that's something we're interested in as well. So one question you could ask to begin with is, can we replace it by something weaker that would, for example, not imply that the beam is Poissonian, because one is interested in sub-Poissonian beams, that is beams with reduced intensity fluctuations. They have particular applications. So yeah, could we replace it by something that could even allow arbitrarily sub-Poissonian beams, this condition? And the answer turned out to be yes. And amazingly, this actually allows an increase in the coherence. So in fact, allowing the beam to be sub-Poissonian gives us an increased coherence by a factor of 4. And this is something which has just come out a few days ago in PRL. And again, so this is, so my PhD student, Lucas, is the first author on that paper there. Okay, but then one could go even further and say, well, let's not just use a weaker version of that. Could we actually drop it altogether, that condition 4? And that's an open question. Okay, that's something we're still thinking about. And my feeling is that one might have to then use a different coherence measure to get something sensible if one does that. Okay, then on the experimental realization part, so as I already mentioned, we have this collaboration with the French group to actually try to realize this in QIQT. So we're putting a lot of thought into what would be the most feasible way of doing this. And then we could also ask in the optical frequency range, is there some other mechanism other than the super-radiant one which we came up with for having a super-duper laser, right, that could surpass the standard quantum limit. And that's all, I think. Yep, I just have appendices after that. So thank you very much, and I'm very happy to take questions now.
Yeah, thank you, Professor Wiseman. And now the session is open for the question. Please go ahead one by one for asking questions.
I have a question, Satyavat.
Yeah, sure. Please go ahead.
How does the beam profile look like, particularly the Wigner function?
The Wigner function, did you say?
The beam profile, namely the Wigner function, does it still look like a Gaussian for the output, or?
So do you mean by beam profile, do you mean like a transverse beam? Do you mean like in space? Is that what you mean?
Wigner function, the Wigner function in the phase space.
Oh, okay. So in phase space.
Yes.
So yeah, it's not core. I mean, it's harder to answer that question because we're talking about a beam is an infinite dimensional. I mean, what I mean, it's not a single mode system. It's an infinite, infinitely many harmonic oscillators. I have a continuum of harmonic oscillators described by, if you like, described by this. Where did I get to? Yeah, I think it's here. Right. So I don't just have one annihilation operator or whatever. I have a whole family parameterized by this continuous parameter T. So it's a little hard to say, yes, how would I, I can't really draw a Wigner function for the beam because of that. But under the condition that, let's say, well, let's at least say that the intensity fluctuations, right? If given that it's well approximated by, if you say that the second order Glauber coherence function well approximates that of an ideal laser beam, which is basically just by saying it's a coherent state, then that means that in terms of intensity, it's exactly like a coherent state. Okay, so we'll have exactly Poissonian distributions. If you could sort of look at the intensity in phase space, it would be exactly Gaussian, if it were possible to satisfy that. Now, in phase, it's a little harder to do because it sort of intuitively over short times, you could think of it as being Gaussian in that direction as well. Like if you could linearize this phase diffusion, then yes, it would just look like starting as a coherent state and getting, staying Gaussian, but getting broader in the phase quadrature over time. And yes, that approximation works for some purposes, but for other purposes, one has to take into account that over a long enough time, it's not Gaussian because the phase actually diffuses over a large part of the circle. So I hope that answered the question.
Got it. Thanks. Yeah.
So any more questions? So you can write in the chat box or you can ask directly. So it looks like there's no more question. Unless, yeah, okay. Yeah, who's speaking? Yeah.
Can I ask?
Yes, yes.
Yeah.
Yes, please go ahead.
The limit is proportional to for the initial classical limit. It was proportional to mu square, and now you show that it's proportional to mu to the power of 4.
Yes.
Is there any relation that may be more precise? That is a combination of these two dependence.
Sorry, is there any what? Sorry.
Formula that would combine mu to the power of 2 plus the term with mu to the power of 4.
Oh, you mean so like
more general one?
Right. I mean, so you're saying like, can you sort of think of it as being the addition of two terms, and right, and if your mu to the, if mu is large enough, then the mu to the 4 dominates the mu squared. Is that sort of what you're asking?
Something more general.
So yeah, okay. I mean, so the answer is that would depend. Oh, yeah. I mean, I guess so we didn't, for this model which we just constructed out of thin air, so to speak, just to achieve the Heisenberg limit, we didn't look very much at the small mu limit because we were really interested in getting this power law. Okay, but for the super radiant, the super pumped and super radiant model, for that we did actually look at exactly what it looks like as a so it doesn't achieve the mu to the 4th, but so the blue is the exact numerics. The red, I should have said probably, the red is the analytics. So this just shows that the analytics actually works pretty well, except down here. But that's what I've said, we don't care, but we can, so it's sort of interesting, I think, the way it behaves. It's less trivial than one might have thought, that for very small pumping, it actually is just equal to what the Schawlow-Townes limit says, but then that's just because that's essentially, that's terrible. Okay. It sort of has this plateau here, okay, which I find interesting. So that plateau suggests it does have a slope, but if you squint a little bit, it does sort of look as if it plateaus for a bit and then goes to a different scaling. Okay, so that plateau, because of the way we're plotting it as the coherence essentially divided by mu squared, I think that's evidence that initially it sort of is it's looking something like mu squared, but then as mu gets larger, you start to see this different scaling. So we have a very complicated analytic expression and the numerics, of course, which has all of that in it. But yes, but I don't think it looks. I haven't looked at it in detail. I don't think it just looks like a mu to the squared, a mu squared plus, well, in this case, mu to the 8/3 or something like that. But yes, you can interpolate between them, yeah, and it does interpolate between them as you increase the pumping. For this sort of physically reasonable model, that below values of pumping, it's behaving more or less like a standard laser, a standard ideal laser, where you get this value of 2, which is the standard quantum limit. That's what this dashed line is. But then, yeah, as you go to high mu, you go into a regime where you have a different scaling rule.
Yeah, I thought it may also depend on mu to the power of 3, as it was shown as earlier experimentally. So in general, maybe it may not be polynomial form, but it's some function where in the some limit is expanded in terms of
Okay, so
polynomial.
I guess I don't know what the mu to the power of 3 experiment is that you're referring to. So, I mean, I'd be grateful if you could share that. Yeah.
One of the paper that show it depend on mu to the power of 3.
Oh, so I should have, yeah, maybe I wasn't clear with that. The mu cubed paper, that was not an experimental paper. I mean, it looked like, yeah, I mean, they are an experimental group, and that's probably why, yeah, this looks a lot more real than our our pictures here, because we're really theorists. Most of the authors on this paper, I think, were, or certainly some of the authors were experimentalists, but this was still just a theoretical paper. This was a proposal for how this might be achieved. Yeah, it wasn't a yeah, it wasn't an actual experiment. So we are still, yeah. So I think the race is on now between this experimental group and the one that we are collaborating with to see who can show a beyond standard quantum limit coherence first.
Okay, thank you. Thank you very much.
Yeah, thank you everybody. So we are actually running a little bit late, so thank you.
Yep.
Professor Wiseman. Yeah, Professor Sinha is already joined. Yeah, so that we can check.